Today is talk about our GVERSE Geomodeling tool and talk about a particular feature of that tool. One of the modeling options that you have called surface constraints or conformance. Okay, and I'm going to use to show you its power. I'm going to look at three different geologic scenarios, three different projects. The first one is going to be toplap unconformity, truncations, and a prograding and downstepping actually succession in the late Paleozoic in Oklahoma. And then channel truncation using an example from the early Pennsylvanian, lower Pennsylvanian of eastern Colorado, the Morrow. And then I'm going to demonstrate the use of a seismically derived horizon to constrain relatively poorly controlled surfaces, including a horizontal drilling target zone. Show you how that works. Okay. All right, without further ado, let's get into the demonstration here. Let me minimize PowerPoint. As a refresher, if you will, for those of you that may be familiar somewhat with surface constraints or conformance, or an introduction to it for those of you that haven't used it. This is a schematic from a document that was put together early in the days of what has become GVERSE Geomodeling, earlier called kind of smart section second generation. And it shows you three surfaces, A, B, and C. Surface A is well controlled. You notice there's picks in all the wells there, those vertical lines. Surface B is less well controlled, and surface C is very poorly controlled. And within GVERSE Geomodeling, each of these surfaces is typically displayed using well-based data, right? Either in map view or cross-section view. And so the relatively poorly controlled surfaces kind of go off and do their own thing relative to the surfaces that have more control. So what you can do is, in this example, you would use surface A to constrain surface B and surface C. Now, as a geologist, you have to make a judgment call and say, yeah, surface B and surface C are essentially concordant with surface A, so it's legitimate to go ahead and constrain them. You wouldn't want to do this type of constraint across, let's say, an unconformity, for example, where the surfaces might actually not conform across that unconformity. So you have to use your best judgment in that regard. What you end up with when you do that conformance and apply the tool, let me drop down here, is you would end up with the two relatively rogue surfaces, B and C, going ahead and behaving themselves and actually conforming to surface A. So again, that's a little bit of a schematic. Now what I want to do is go ahead and launch into a real world example in that Oklahoma, late Paleozoic Oklahoma example. So here we are in GVERSE Geomodeling. Let me pop into the map view. It's a pretty simple project. It's got 23 or so wells in it. And this is a single cross section that I was just showing you. I'm going to go ahead and on the left side here in the data panel, I'm going to double click on my webinar cross section to bring it up. There it is. And just as again, a quick review of conformance, how you set it up and how it works. I'll take a look at this area on the right side of the cross section. I'll go ahead and zoom into that. And what I've done here is I've gone ahead, just to demonstrate this technology, in this case, I've picked this blue surface in 3 or 4 wells across here, and you'll notice that it's not behaving itself relative to the other surfaces. Excuse me, I picked a little flooding event right through here using the resistivity log as a guide. And notice that in areas where it's not picked, what it's doing is it's interpolating a dashed surface. These can be clicked on and dragged and placed in the proper spot. It's actually predicting where that surface should be based on very limited control. So what I can do is I can say, okay, I've got a really well-controlled surface down here, this OFL 247 surface. I can go into my geosurface model properties dialog and set up conformance between my using my well-controlled 247 surface to constrain this poorly controlled CS2 surface that I've picked. So let me go ahead and do that as a quick demo. I'll go into Geosurface Model Properties, okay? And there's a lot of units in here, so you can see you've got to kind of pick through them. I'll go to the Surface Constraints tab and find my CS2, and again, let me just refresh my memory here. The 247 surface needs to be used to constrain CS2, and notice you can constrain both upward and downward, and you'll see that in my toplap example here in a second. So 247 is going to constrain CS2. Back to Geosurface Model Properties, Surface Constraints tab up here, and I'll take CS2 and drag it on top of 247. So that sets up a conformance relationship, and the default here, notice you've got a lot of options here in terms of how you do the constraint. The default option is usually what we stick with, and that's just to use the complete isochore thickness trend that geomodeling recognizes whenever you have hard point control on both surfaces, okay? So I'm going to say okay to that, so that is set up. Let it go ahead and do its thing. And essentially what that means, what that isochore thickness trend is doing, is it's creating an isochore in memory, okay? Got a lot of surfaces here, so it's taking a little bit of time to go ahead and set the model up. Let me go back and get that cross section up. It likes to misbehave occasionally. Okay, so any place you have hard point control, like in this well here and in this well here, it's going to use the thickness trend it sees. What I need to do now is go ahead and apply the conformance tool. There's your 5 geomodeling tools up here: fault, offset, conformance, unconformity, trimming, fault, and unconformity networking here. I'm going to go ahead and apply conformance and hit the check mark to go ahead and turn it on. And what we should see is, there we go, the blue surface, CS2, conforming to 247. So that's how conformance works in general, okay? And that'll give you a much better idea of where that surface actually belongs. And then again, you can come in and grab the dash lines and move the surface to the actual correct location. All right, fair enough. Now let me go back out to the full cross section again. The unit I'm going to look at next is this upper unit that's prograding from and downstepping from left to right. Okay, this is a succession that's probably responding to a glacial eustatic fall. This is, again, late Paleozoic stuff. And what I want to concentrate on is this area to the left here where we have a toplap relationship developed. So let me go ahead and zoom in. Okay, so you'll notice this red surface, which is picked through here, is jumping up above what is recognized as a flooding surface. It might also be a subaerial exposure surface. I don't know. I haven't looked at these rocks in outcrop or core, so I'm not sure about that. But in any event, it's at least a toplap surface where these surfaces merge with that subsequent flooding surface. Okay. Now you'll notice that they're jumping up above that. And what I've done here to set this up is I've defined this master flooding surface right here as an unconformity, so that if I can then constrain both the red and the green guy here by this purple unit, which actually is picked all the way across, and then apply unconformity trimming, you will get a truncation, basically a toplap truncation of these two surfaces, red and green, at that flooding surface, okay? So what I'm going to do is I'm going to go back to Geosurface Model Properties, and the purple surface that goes all the way through is actually 346 here, and then the other two are 345 and 349. So I'm going to go up to Surface Constraints, and I'm going to drop 345 on 346, and I'm going to drop 349 on 345. So it's a stepwise conformance, and I'll go ahead and say okay to that. And what that does is it it forces those surfaces to conform to a well-controlled through-going surface that's been picked below them. Again, you can constrain either up or down. Okay. In most cases, you'll probably use conformance to constrain downward. We can go upwards as well. Okay, let the model do its thing here. And again, the little trick is to double click on your cross section and bring it back up. So you'll notice that the surfaces are not quite so rogue, the red and the green here. They're more or less conforming to the purple surface. However, they are, I do want to use another modeling tool here because they're jumping up through that flooding surface. You notice the dashed lines, meaning they're not picked as hard points, but they are showing up because I do have surface projection on. Now what I'm going to do is I'm going to turn on our unconformity trimming tool, and geomodeling will recognize that these surfaces are banging into this younger unconformity, this flooding surface unconformity, if you will. And let's watch what happens when we do that. I'll update the model. Okay. And notice now that we've got our toplap truncations defined by the geomodel. So it's predicting where the green here and the red surface here are going to truncate against that unconformity. And I could do more surfaces if I had more correlations, let's say to the right or down dip, if you will. Okay, what about looking at these intersections in map view? Well, you may have noticed briefly when the map popped up that we had a couple of new lines on there. And again, these are 345 and 349. I'm going to go to the map right here, the map window right there. And what we're looking at down here to the southwest is the intersection of those surfaces with that flooding surface unconformity. So here's the master flooding surface. Notice the little plus sign next to it. If I open that up, it's going to give me correlation unconformity intersections. It's recognizing 5 of them. And I've turned on the 349 and the 345. Okay. The green one and the red one. There they are. And if I wanted to actually look at the 349 structure map, I could turn that on as well. That's right here. Click that on. There's the 349 structure map, and you'll notice that the 349 surface is recognized to truncate to the southwest. In a like manner, I could turn on the 345. I'm sorry, the 345 surface. Where are we? Turn off 349. Turn on 345. And it is present in most of the area, but it does truncate to the southwest. Okay, so again, in map view, I can see these truncations. Again, I don't have a lot of control, obviously, away from my single cross section. You can see there's no wells in here, and that's why the line is stopping. But you notice that the surface doesn't stop. It does stop. Okay, so that is one example that you, in terms of using the conformance tool, that I find pretty useful when you have that kind of a succession. And it may be that in some cases, let me go back to my cross section here, right? You could have a sandy, and you actually do have some sand in here. So there is a potential up dip pinch out, depending on what the structure is exactly. There is a potential up dip pinch out of this sand right here, and you can map it using geomodeling. If you had a lot of control, you can get a pretty good idea where that pinch out might be. Okay. So I'll go ahead and close this cross section. I want to go to another project now. So let me pop up Project Explorer. I have this Moro project that I'm going to activate. And that's the channel incision, and I'll go through this one in a like manner. Let's see what else. Oh yes, geomodeling says, hey, I gotta open a new project, and I've got a webinar interpretation here. Let me open that. So again, this is another similar, this will be another similar use of, another similar use of conformance in a different geologic scenario, a channel incision. There we go. Let me zoom into my area here, use the zoom tool. This is the area where it's all happening. And again, I've got a single cross section to show you right here. I'll go ahead and open the cross section from the map. There we go. And I'm going to zoom in to this area down here to the lower portion. What we've got here, if you notice, is let me go to surfaces over here. We've got the valley base of the Morro picked in a number of wells right here. Notice it's dashed over here, meaning it's extrapolating it. It's not a hard point pick. And I'm going to go ahead and date them by hitting the space bar here and a flooding surface above that Morro Valley. So the scenario here is that you've got a Morro Valley base unconformity, okay? And then we've got a flooding surface up here that's also defined as an unconformity. And then we have some marine markers that are picked in the normal succession. And you'll notice that the marine markers are dashed in here because they have in fact been chopped out by this channel. So what do we need to do here? How is this set up? Well, if I go to Geosurface Model Properties, Surface Constraints, we're already set up with the flooding surfaces constrained. All right, so I haven't got conformance on. You notice the little yellow button here is not depressed. So the conformance is not actually taking place yet. The other setting in here, and this is relative to the channel form unconformity, is that we have networked the two unconformities such that the flooding surface is networked to this Morro Valley base, with the Morro Valley base being subordinate to the flooding surface. And the other key aspect of the setup of this little project here is that the Morro Valley base is set up as an unconformity here in the Strat Column Manager, and it's reflected in Geosurface Model Properties under the Surfaces tab. In addition, it's set up as a channel form unconformity. All right. And geomodeling understands that. So when I turn on conformance and unconformity networking, watch what happens. Now the key here is actually, let me turn on conformance first. And what you'll see is that these units are going to go ahead and these flooding surfaces are going to behave themselves a lot better. They're being constrained by this upper flooding unit. Again, in a normal marine succession, the idea is, yeah, these flooding surfaces are more or less concordant with one another, more or less parallel or subparallel. And so they're behaving now. And now what I need to do is go ahead and invoke a couple of more tools, right? Unconformity networking and channel truncate, unconformity trimming, which will let the channel go ahead and cut these guys out. So let me go ahead and update the model. Let's do its thing here. And so there's the Morro channel. And again, I had to set the Morro Valley base up as a channel form unconformity for it to behave like this. Essentially what it does is it says, okay, I don't have a Morro Valley base in this well number 3 right here. What I need to do is cruise up and bang into this flooding surface unconformity between these two wells. Otherwise, if you didn't have it set up as channel form, it might go running off and extrapolate itself more or less based on this geometry that you're seeing here where it is picked. And notice again that you've got truncations of these marine markers now against that channel. And just like in the toplap example I showed you where you can see that in map view, let me go back to map view here. Well, what we've got here is the Morro Valley base correlation unconformity intersections showing up. The V7, the V9, and the V10 flooding surfaces are all showing up. So you can actually map out where those valley edge truncations are in map view. And if I want to see a structure on the base of the Morro Valley, I can turn that guy on, and there's your Morro Valley base structure in gray. Okay. So again, it's critical to use the conformance tool to get those marine markers to behave themselves, because in areas where they were chopped out, they weren't picked, obviously, they're gone, and they're going to become rogue if you don't constrain them by a through-going flooding surface, in this case, the overlying V7, okay? All right, so that's example number 2. Now, I want to go to example number 3. I'm going to go ahead and close my cross-section. Back to Project Explorer. And example number 3 is going to be taken from our well planning and geosteering training project. I'm going to go ahead and activate that. This is a pretty simple, straightforward example of how you can use conformance associated with a seismically derived surface to get a much better handle on exactly what's happening with regard to underlying surfaces that you might not be able to pick in seismic. So let me go ahead and I'll go ahead and save changes to my little webinar interpretation. There's my webinar interpretation in the well planning and geosteering project. Let it come up here. There we go. And I've created so we have a relatively simple set of stratigraphic units here. If I go to Geosurface Model Properties up here, click on Model Surface, you'll notice I've got some Atoka, Barnett markers, Ellenberger, and this funny thing called A from SV. So the A, actually I don't necessarily want to model A, I don't think it's even in here, no worries. The A from Size Vision, this is SV, Size Vision, now GVERSE Geophysics. These guys, right, are all sourced from well-based data, okay? If I click on each of these, you'll see that. Whereas the A from Size Vision is sourced from a seismically derived isomap layer, all right? So what we did in petrophysics, in geophysics, is create an isomap layer from a seismic horizon, this A smooth horizon in depth, okay? And I'm sourcing the A from SV surface from that grid. Now, you can also go directly to your seismic interpretation and source it from a horizon if you wanted. You do something like this right there. I've chosen to do it off the grid, okay? And I've also gone ahead, and I'll show you how this works here in a second, constrained these other well-based derived surfaces in geomodeling, constrained these to the A from SV, the geophysics derived surface. Okay, so that's how this guy is set up. I've created an arbitrary section through the geology here. You'll notice there's no wells involved actually, except for this little stub well that I would plan. I just wanted to show you that you can use this, and this is typically a technique used by people when they want to perhaps plan or geosteer. I'll go ahead and open this cross section. Okay, and notice it's a pretty straightforward setup here. There's my little stub well number 2 way up here. It's got a TD of 100 feet, which is typically what you want to do when you're using our well planning tool, is create a little stub well and then pick your target points in the cross section in the geomodel, right? And it generates a proposed directional survey, etc., that you could feed to your drilling group, etc. Very common workflow technique. Now, what you'll notice, however, and I'm going to zoom in down here, this is the area that I would plan the well, let's say. And you'll notice the surfaces I've got displayed here are the basal Atoka down through the Barnett. I don't have the A from the geophysics displayed right now, okay? Now, I'm going to go to GeoAtlas, and I'm going to go ahead and open my little webinar map here to show you what that surface looks like that came out of seismic, came out of geophysics. It's a very detailed, it'll be a very detailed surface. It's called the A smooth horizon. There it is. That's what I'm using to source my surface in geomodeling. Let's look at it in map view. I'll turn it on. There it is. So you can see that it's quite a complex surface, whereas the surfaces constrained, or I should say defined by well control, are much simpler. Okay. So this is a very good surface to use as a guide, let's say in well planning or in geosteering. So I'm going to go ahead and minimize GeoAtlas. And what I'm going to do next is I'm going to turn off the basal Atoka sourced from well base and turn on that same basal Atoka sourced from geophysics. And you'll notice it's a much different looking surface through here. Okay. Again, the seismic control allows that surface to come out in all its glory. You can see the surface is much different from the well-controlled surface. Now what I'm going to do is I'm going to turn on conformance, and just as a reminder, in Geosurface Model Properties, surface constraints, I'm using that surface to constrain the underlying units here that are only controlled by, well, we couldn't pick them off seismic probably, right? This A surface was a fabulous reflector. So when I turn on conformance and click the little check mark here, watch what happens. So all of my surfaces are now conforming to that atoka defined by the seismic. And now I could come in here with my well planning tool if I wanted, and I could go ahead and plan my well. Let's say it's between the Barnett maximum flooding surface and the upper Barnett that I wanted to drill my horizontal. Now I can come in and put my target points along here and generate that generate that proposed directional survey, feed it to my drilling group, whatever. And again, a really powerful use of conformance technology within GVERSE geomodeling. So giving you 3 examples of how you can use conformance in terms of toplap, and if you wanted to, you could use that for downlap as well, or onlap onto a paleo high. I've actually played that game in the central Kansas area where you have the central Kansas uplift and the Pennsylvania units are banging into that central Kansas uplift and pinching out. There's a lot of plays associated with that. Conformance tool will allow you to get a good prediction of where those are. So toplap, onlap, even downlap, of course, you could truncate against a what's defined as a downlap unconformity, and then the channel form unconformity, incised valley or channel, where you can constrain the marine units by a flooding surface that is present across the entire area, again assuming that you believe there's concordance there. So that's another use of it, and then the channel will truncate those and you'll get an accurate rendition of where those units are on the map, those truncations are on the map. And then thirdly, another example here, using a seismically derived surface. And just to show you that it really is seismic, there's my seismic backdrop in here. Turns out there's a little fault there. That's why this thing is kinking down. But there's the horizon that guy is based on. I'll go ahead and turn the seismic backdrop off. So there's, again, that isomap grid source surface, if you will, constraining these guys. So I appreciate it. I hope that you picked up some tips here with regard to GVERSE geomodeling. I know that you can go ahead and send questions to Christina, or if you have additional questions, feel free to email me directly at jfrench@lmkr.com, jfrench@lmkr.com. Be glad to answer any questions you have. Or in addition, I would be glad to have a screen sharing session with you if you wanted to set something up like this.